So chapter 32.6, the RLC circuit. Okay, so today, or this part of today, we're going to turn our attention to a more realistic circuit, which involves all of the circuit components that we've been dealing with, the resistor, the inductor, the capacitor, to a more realistic circuit. And this circuit is an analog to a mass on a spring system that's, going up and down or back and forth, but there's some kind of damping or resistive effect. So it's slowly going to, stop its oscillation. It's basically, it's going to slowly come to rest. And that's due to a damping force, air resistance. Maybe the mass spring system's in a liquid of a high viscosity, and then it's just like it starts to damp. That's basically how your shock absorbers in your car work. They're mass spring systems, at least the ideal of them are, but they damp. There's damped harmonic motion due to some sort of lubrication in the shock absorbers that causes them not to just keep on bouncing when you hit a bump on the road, because that would be bad. You get sick inside, you just keep bobbing and bobbing and bobbing. So the shock absorbers, very large spring constant, liquid in there, keeps the oscillations just at a very minimum and a very short amount of time. So shock absorbers are definitely the, let's say, the mechanical analog of what we're going to see here in our RLC circuit, because like the RLC circuit is basically the electrical analog to that damped mass spring system. And we're going to see that play itself out. So our realistic circuit, because I just say it incorporates everything. It incorporates all of the circuit elements, most important circuit elements, or baseline circuit elements of your physics classes or your electrical engineering classes. There are other components like LEDs, diodes, transistors, but we'll leave that. Well, that's something you commonly talking about. We'll talk more about in your electrical engineering classes or even advanced electrical engineering classes. But these are the three most common components in your realistic circuit. So this RLC circuit consists of a resistor, an inductor, and a capacitor. So we then just draw a simple circuit diagram. We have battery, our power source. And then we have, say we have a switch here. This guy's connected there. We come all the way down to this capacitor. That's going to be it's going to be building up charge at t equals 0. You flip the switch. This capacitor has now a maximum charge. We've taken a look at that yesterday, and we call that maximum charge Q max. And then draw it all the way, carrying along. And then now we have this branch consisting of a resistor, and then a inductor, which is a curling wire. Can't really draw that vertically, but that's our inductor, and this is our resistor. Then carry on here to our voltage source, positive, negative. I believe now we understand the flow of conventional current will be this way through the capacitor, and this is our RLC sample circuit in parallel. Well, at t equals 0, the switch is flipped on. The capacitor is at maximum charge, Q max. And if the switch goes to B, okay, well, I didn't label those pieces. And this is A, this is B. If the switch goes to junction B, our circuit will look something like this. It's the charge flow. We go all the way here. Here's A. And then we connect everything up like so. So this is our switch. Make sure I make different colors. And then the current just reverses. When we leave the battery out, it just goes the opposite direction. We're changing the polarity of the capacitor as a result. And this is something that we've seen when we were looking at the RC circuits. When we were discharging the capacitor, the current goes the opposite direction. So same idea here, same physics as it were. So positive, negative this time, because now we have a reverse of polarity, whereas before we were going here. And the second case, let me finish drawing everything out. Okay, so we have resistor and then inductor, and connected there. And go all the way to the battery. Well, the battery is not part of this setup here, but now the current goes in the opposite direction. It switches around. And we know that the inductor's main job is to create its own EMF, self-inductance, but now we have an inductor that does the job principally. So as the current goes this direction, there is a back EMF that goes that sets up a current that goes in the opposite direction. So now the back EMF, you know, if you want to just play around with that, it'd be in this direction. It's going to, you know, slow this new direction of this current down in this direction, whereas over here, it would slow it down in this direction for this particular circuit here. So the EMF is always going to slosh back and forth. And now we're kind of forcing the oscillation by closing the switch at A here, then closing at B, go back to A, you know, back, forth, that'll cause this sloshing action of the current, this oscillation that we were talking about yesterday. And then we're going to see that even more organically from an alternating voltage source. So you basically just think of a battery that's now on its own going to switch its own polarity. It's going to slosh one direction, slosh the other way, positive, negative one direction, then it reverse the positive, negative polarity. Generators are good for that, or some kind of electrical oscillator where you can just play with the voltage. The voltage is now going to oscillate to and fro. Whereas in this case, this is all direct current, but we can force the oscillation by opening the switch at A, closing it at B, back, forth, slosh, and you know, we can induce that oscillation that circuits normally have. Those circuits that would basically would have no net loss in power, and we want to talk about that. And that's what makes the AC circuits most powerful, because there is no power loss for, you know, relative to DC circuits. That was the triumph, at least one of the triumphs from Tesla using AC current or AC circuits, that there is no power loss, because you're going to get the same current in one direction. So the time average is going to be equal to zero. You're going to have the same positive magnitude in current. You're going to have, whatever the magnitude in the positive direction for current is going to be the same magnitude in the opposite direction. So when you time average those two, you know, the area under those curves is going to net out to zero. It's not going to be any power loss. So AC circuits are the best as far as usage, energy usage. Whereas direct current, over time, you're going to build up power loss. So that's why, you know, your power plants are designed to produce alternating current. And then you have, at your power outlet, you have a converter that takes AC and converts it to DC, because, you know, most of your appliances are going to run off of DC. But the main energy source, the source of the current to your homes, is all alternating current. All those long power lines, alternating current. So it's a major triumph from Nikola Tesla. So in this case, we have a switch here. It closed at B and the current reverses direction. And yeah, so let me continue with that. Okay, so let me do this. Now, if the switch goes to B, in that case, let's go over here. Switch goes to B. The total energy in the inductor and the capacitor is given by the equation we've seen before, given by, U for energy. The total energy is Q squared, Q squared max over 2C plus 1/2 Li squared. We derive these equations for the energy usage in the capacitor and the inductor. And because the capacitor is built on charge, inductor is built on current. So we saw that last time. So those in this RLC circuit, the power across both of those components is given as this sum here. But in this RLC, this power loss or this power usage or energy usage per time is not going to be conserved because now we have a resistor. This resistor here. And the resistors, what they do is they take energy out. Any type of resistance or friction is always taking something away. So the energy is not going to be saved. This is RLC. So we're going to get a power dump here. We're going to get some sort of loss. So I'm going to write that up. But this power total is not constant, so we're going to get some loss since the resistor converts some of the energy from the battery to internal energy. So it goes to heating up the circuit. And here, resistor, you could have like another part of this symbol, like to represent a light bulb. Your lights come on, right? So this is using the energy from your AC outlet. It's converting that energy in that circuit to internal energy that we, register or we can see manifested as light. So that means that this RLC circuit doesn't conserve energy, as the resistor, light bulbs, or any of your appliances are going to take that energy and use it. Turn on the lights, refrigerator's working, etc. So we're losing some energy. Overall, the energy is conserved when we close the entire system, but relative to the circuit, some energy is lost. Convert some to internal energy. And that's, that from friction. Friction's always going to take something away. If we have no friction, then we can close the system off to the environment, and now we're going to have pure conservation. But when we put a resistor in there, we put friction in, air resistance, something is always going to damp the current in the line because some of that energy is lost to the resistor. Now we can represent that mathematically. The energy loss per time across the resistor, it's a net loss, is negative I squared R. We know that that's one of the equations for power when we know the current and the resistance. So this is a representative, the energy loss across the resistor is equal to negative I squared R. That represents a loss of power across the resistor. So that means energy is lost, negative sign. Energy lost to resistor from circuit. And it's all about perspective. The perspective here is the circuit. We're losing it to the resistor. And if we close the entire thing off, the entire thing is conserved. So now the power du dt of the entire circuit, the RLC circuit, in the circuit is given by, so L, Li, di dt. plus Q over C dQ dt equals negative I squared R. And this is just representative. And if we add this over here, it's going to equal 0. But this is saying that the power that we talked about yesterday, this is the power in the inductor and capacitor. Whatever the power is, it's going to be equal to the loss in the resistor. So some of that energy gets lost to the resistor as a negative I squared R. And so if we are, and what we've usually been concerned with is getting an equation for the charge across the capacitor, and then in turn we can get an equation for the current in the entire RLC circuit, which we can do it by taking the derivative of that charge function. And voltage, well, it's going to be whatever the current is times the resistance. Well, in this case, it's going to be a sum total of all of these. But usually we're just looking at charge in the circuit or charge in the capacitor, because not only capacitors are they'll principally, well, they're functions of charge, devices that use charge as opposed to current, and then the inductor, which uses a current. So we're looking principally at Q, get an expression for Q, and then get an expression for I. But yeah, so we'll just get an expression for Q. If you want to get an expression for I, you just take the time derivative and you can get the current in the circuit as a function of time, because again, this is oscillations. Things are going back and forth. You can find out what the charge is going to be at any given moment. You can find the current at any given moment by looking at the results to be in some sort of sine or cosine. So let's convert. So when we convert this equation to a useful form, and let's say our current is going to be dq dt, we are going to obtain, so if this, because we know this from first principles, going all the way back to chapter 27, that's our equation for current. And so that makes the equation Li d squared q over dt squared plus I squared R, right? Because I'm just adding this over here. And then that's going to be plus Q over C I. So this is for the inductor. This would be the resistor. This is the capacitor. Equals 0. So now when we divide through by the current I, we will have L d squared Q over dt squared plus I times R, and plus Q over C equals 0. So this is basically Kirchhoff's rules for this circuit for an RLC series circuit. So we can use the Kirchhoff's rules, loop rules, to get this form. So this is basically, this form here is the voltage, Kirchhoff loop voltage for this RLC circuit. Because we may recognize that this term here, I times R, delta V equals I times R, and delta V is Q over C for the capacitor. And this mess and this deal here is the voltage across the inductor. So we have a second order derivative of charge times the inductor, which is basically the same thing as Li. Well, we've divided through by I, but this comes out to be the voltage. And the form before, let me correct myself, the form before is the power usage. We just looked at that already. So as we've done in several days now, we can take an equation like this and solve the differential equation here Why is it a differential equation? We have derivatives here, and so we can now, if we want to find Q, we have to use the mechanics or the tools of the differential equations to solve for Q. So before that, let's get some appreciation, some understanding for this equation. This is similar to form back in mechanics, d squared x dt squared. You might recognize this as what? What do you think that is? B dx dt plus kx equals 0. Give me some feedback. What do you think that first term is? What does that represent?
Momentum.
Not quite.
Is that force?
That is force. That is a net force, because now d squared x dt squared is the acceleration, mass times acceleration, right? There you go. And then let me just play around with this even more. So this would be the sum of all forces in a mass spring system. Almost there. You said momentum. We got to take another derivative. Get that acceleration. You're right there. Okay.
Yeah, I missed it.
Okay. Don't worry about it. So which, you know, if we were now going to do this in terms of Newton's second law, d squared x dt squared equals negative b dx dt minus kx. Does this look familiar?
Spring.
Yeah, the spring force, Hooke's law. What do you think this is? Something to do with your little, remember that you were coming to me after school, Jeremy, last year, and you had all these different.
Is that something to do with air resistance?
Air resistance is correct. Yes. So these two forces, air resistance plus spring force, at least in a mass spring system, is equal to the net force. And this resistance, or let's say air resistance, is the damping mechanism that brings that mass spring system to 0. It starts off very fast, as you know, depending on how far you pull it from 0. It starts bobbing and weaving up and down, and then slowly it starts to die off due to some resistance in the spring, in the air, whatever. Somebody hit it, you know. So this represents our resistance, a resistive force. This is Hooke's law. Both of those forces equal to the net force. Newton's second law. So now we can get some appreciation for this equation by looking at the analog there, which is the sum of all the forces in a mass spring system. And that's why it's more realistic, because now we're including every element. We're not just ignoring air resistance. Like in an LC circuit, we basically ignored air resistance. But in an RLC circuit, get everything in there. You solve those kind of problems, you're good. You can solve anything. So let's see. If we now take the analog, we can just now say L d squared q over dt squared, and that equals to negative r dq dt minus q over c. We can approximate L as the mass. Remember, see the analog here. Look at that, or at least from here. L is like a mass. It's not mass, but it's analogous to it. And if you think about what the inductor does, it creates its own EMF. It bobs back and forth, bobs and weaves, right? In an oscillating circuit. So if we have a driving force, which you'll see in the next chapter, we have a driving voltage source that causes that inductor back EMF to switch directions all the time. It's going to go like positive, then negative, and positive, and negative, like a mass on a spring, up, down, right? So it's really like that. So the RLC circuit is like the electrical analog to the mass on the spring. That mass on the spring that you've seen in my class, or you've seen in my class elsewhere, the electrical analog is this RLC circuit. This oscillation, this production of power in all of these circuit elements, which is pretty much a or the core in circuits for Tesla coils, or different forms of different a lot of different things, generators, or any very complex device. Of course, so something like a motherboard, we'd have to use other elements like diodes and transistors to do other special functions within the motherboard. But definitely, stuff like Tesla coils will incorporate your RLCs and transistors. May take out one of these, take out an L, put a transistor in there, and have an R and a C. Once you really understand and can appreciate, say, the function of a transistor, you might want to substitute. It's that point being that this is a very real circuit. So this inductor, basically, if you will, oscillates EMF like a mass oscillates up and down. So it gives you a little bit more appreciation of the functionality of an inductor. The R term here is more or less like the, so a typical air resistance equation, negative BV, because dx dt is V. Well, this B is like a parameter or constant of the air. Basically, is dependent on the temperature in the air, viscosity, or some other little components of that medium that are incorporated in this B term. So R is like that. It's like the resistance constant, because your resistor, whatever that value is, that's not going to change. It's going to be constant for that RLC circuit. So this is resistive or resistance constant. I'll just say resistive, or I'll just put that resistance constant. And then 1 over C in this case is like the spring constant, because we have Kx. And the X in this case is the Q, because look at it. We were doing derivatives with respect to Q. So this is X, X again, X. So 1 over C would be the K. And, whatever capacitor you have, that's going to be that value. So this is like your, remember how I like to call this, how strong your spring is? Basically, how capacitive your circuit is. And that's, based on the capacitor. Once you put that capacitor in there, it's not going to change on its own. So those are the analogs. And so how we solve this here, we never really did this back in mechanics, but what we're going to do today is what we're going to do, what we would have done in mechanics with this RLC circuit. So let's go to the next. Step by step this thing. Let's see here. Do this first. Okay. All right, I got that. So let's now bring everything. Let's look at the this equation all added together. So I'm going to do this at step 1. I'm going to say this is L d squared q over dt squared plus r dq over dt plus q over c equals 0. And the second thing I'm going to do is I'm going to get rid of this L. I'm just going to have this function here, or that derivative all by itself, and let it equal everything else. So d squared q, just like we did with the first order differential equation, we have dq dt, and then bring all the q's together. So we have to do like kind of a middleman here. Plus we have another term. So this is going to be equal to negative r over L dq dt plus q over LC. And then do this very explicitly, not assuming anything from you guys. Oh, this is going to be minus, sorry. Because we bring it over there. And r over L q dt plus q over LC. And that's what we're gonna work with that. This equation looks like a quadratic, AR squared plus BR plus C. Look how beautiful that is. We are using our basic principles of the quadratic equation to solve this differential equation. And so stay with me on that. So step 5, we are going to solve for r. It could be x. R is just variable we use. Don't matter. R equals, in this case, it's going to be negative b plus or minus. And that b in this case is r over L. It's going to be plus or minus. Let's squeeze this in here. It's going to be r over L squared, b squared minus 4ac. Well, the a is 1, and then the c is going to be q over L. Well, it's going to be 1 over LC. Remember, the q is the x. You're familiar with this. See how that stuff all comes back in physics. So that's going to be minus 4 times 1, squeeze in here, 1 over LC. All right. Now it's going to be multiplied by Q, because remember when we were doing the first order differential equation and we came out with the square root of negative omega squared x. Okay, well, x is that variable that's not going to be under the square root sign. We introduced r and omega to represent the real variables in the equation. So this is a representation of what's going on in the equation here. So r and this stuff, and then it's all multiplied by q. So we'll be dealing with q in a second. So we'll deal with that. So this is going to be negative r over L plus or minus, and we do the square root of that. It's going to be r over L minus 2 over the square root of LC, and this is all divided by 2, divided by 2a, sorry, there. 2 times 1 is just 2, and it's over 2. And this is a r, and then there's a understood q hanging out there. Okay, r equals that. So now if we, be careful and just, get rid of this 2 in this fraction, it's going to be r equals negative r over 2l plus minus r over 2l minus 1 over the square root of LC, because 2 divided by 2 here would just be 1. And then that's all equal to Q, or not equal to Q, but multiplied by Q. This being multiplied by Q. Now, let me make a slight correction here. Just this part is multiplied by Q because, again, as I mentioned correctly, all right, that this here is basically taking the place of that omega that was underneath the square root, and that's the stuff that's multiplied by Q. And this stuff here is not multiplied by Q. It's just, you know, negative B. It's outside of the stuff multiplied by Q. Okay, Q, and then so therefore this goes away, and we basically have that. So it's simplified. And then step number 8. We're ready to pretty much integrate. This process, if you look in your calculus book, when any calculus book, like I know the Stewart book, but it depends on what calculus book you're looking at. I think chapter 18 talks about just the process, the mechanics of how to do problems like this, and this is just an application of that. So it doesn't go through the full solution. Like I've seen like so many examples or several examples of people that get to say this point, and then they say, oh, well, now let's substitute some numbers in. Well, we're going to make some assumptions. It's going to be this form. No, be rigorous and solve it out one time. Just do it once, you know. It's good for you. Negative R over 2L plus or minus this stuff here. And they just say, it's cumbersome. What's that? Okay, so now we get back here because remember R squared was D squared dt. R is this. So now we can do the solution of this differential equation. And let's Q here like we did before. We just have, it's just messier. You know, same idea. So now let's just do this. Let's get the Q's all together. dq over Q, see where this is going. And then the dt's, negative R dt over 2L plus minus. I'm just going to do the same stuff here, squeezing out here, Q. So do that same thing. This capacitor at t equals 0 is at a maximum charge. So we're going to go from Q max to Q. And then that's eventually going to so-called bleed into current across the inductor. But it's sloshing back and forth, so it doesn't really quite die off like the LC circuit without a, an alternating source. But this still doesn't have an alternating source, so this will eventually die out as well. We'll see with the AC case, it doesn't die out, it just switches polarity, it switches, direction of charge or the electric field, back and forth, back and forth. So that's what was so brilliant about the ACs, again, is that no power loss. At least the power loss is so negligible compared to Edison's direct current that it's most cost effective to use alternating current. But they didn't want to acknowledge Tesla and that and other stuff. Jealous. Okay, so 0 to t dt plus or minus R over 2L. Dude was brilliant. Just savage. 0t dt. Sorry for squeezing that. Let me write that better. I gotta tell you, just in recent years, I have the greatest appreciation for Tesla. I didn't before. I just kind of heard of them and stuff because they make you know, it's a concerted effort to kind of blot him out. And there's other stuff that's been blotted out. There's a whole realm of physics, plasma physics, that doesn't get as much play. And I know why. I'm not going to go into that here. 1 over square root of LC 0 to T dt. And you see where this is going, right, guys? We've done this before. Natural log Q over Q max equals negative R over 2LT plus minus, all right, R over 2L and that's square root of LC T. And then I'm just going to continue Q over Q max. We divide both sides by natural log. We're going to get e to the minus r over 2lt. And this is going to be, so this plus or minus here, and approximate it as a cosine function. It's cosine and sine functions, but sine goes to 0 when t equals 0. So the cosine is the one that remains. It's really sine plus cosine. Remember, this is, switch is closed at t equals 0. So we're going to call this cosine omega d for damping frequency times t, where the damping frequency yeah, let me finish this part. Okay, there's that. And then, yeah, because I want to get my Q. Q is a function of time. Q max e to the minus r over 2lt cosine omega dt. And that is our equation for the charge as a function of time for an RLC, it's included in there, circuit, where omega d is equal to SR over 2L minus 1 over the square root of LC business. Remember with the LC, it was just one, the omega, the angular frequency is 1 over square root of LC. Now that we have a damping force in there, we got an extra term, R over 2L. Nasty, nasty evaluation of that quadratic, but necessary and very powerful, and you know, a nice application of it. Questions? Kind of follow, really follow?
Yeah, kind of follow.
Okay, you have any specific questions? Or
No, not yet.
all right, always ponder it. You know, something that definitely, you definitely want to be able to go through this once yourself. And then once you see people hand wave their way through, oh, it's approximated, we're going to assume that you can just take it for face value, and because you know how to do it yourself, if you had to do it longhand. Because most people will do that for this particular circuit, RLC circuits, because they don't want to waste the time. You know, they're just bored or whatever. But gotta do it at least once. So the charge on the capacitor, so it experiences a damped oscillation, if you will. It's basically the current in the circuit gets damped over time. Like a mass spring system resistance. very beautiful. You know, really look back and appreciate what's going on here. And there's an oscillation for sure, due to the switching, go from A to B switch. That's just to approximate the oscillation, but we can get that under, you know, normal circumstances without switching. So that's the viscous medium. Okay, some other things I want to say about this. So in the omega D term, in the term for omega D, when the second term, R over 2L, or the first term, when that goes to 0, you know, the oscillation, or the damped oscillation basically becomes the angular frequency of an LC circuit. Well, let me, you know, correct this little slight substance. Since this is a function for charge, we experience that the charge is going to degrade over time. That's what we solve for. We solve for current. We can take the derivative of that to get the current. So that's what's getting damped. Damped circuit has an angular frequency equal to 1 over square root of LC. So then because now I equals dq dt, we're taking the time derivative of a damping charge. Okay, the current is also gets damped, so everything damps, you know. And we're going to get a few cases. One second. Okay. Well, we're going to get a few cases where there's a certain type of damping. In one of three cases, there's basically very minimal damping, there's critical damping, and then there's over damping. And then in our situation, we're looking at the first case where there's, you know, steady damping through time. It can be a case where the circuit experiences critical damping, where you can dampen at some point, it doesn't damp anymore. It doesn't oscillate anymore as the circuit loses charge over time. Then there's over damping, where you might have one oscillation and it's over. You know, it's so damped. It's that resistor force is so strong, like you just bob once. Okay, can't do anything. It's too viscous. Okay. So get what I mean? Well, I mean, at least this is concept. So let's just take a brief look at what that means, how that looks mathematically. From Q equals Q max e to the minus RT over 2L. It's multiplied. I'm going to use that multiplied by cosine omega dt. If in fact the resistance was so strong, there's a great deal of damping. You know, your Q will just go to zero just pretty immediately. We don't have that. That's the case. That's a case of over damping. I'm trying to think of the first term. That's why I was hesitating. The first term, the first situation would be just regular damping. There's another term for it. And then there's a critical resistance. There's a point where the resistance in the circuit basically is in the same amount as the oscillation, and it just stops oscillating at a critical point. So that's all I'm going to say about that, because I want to move on to AC circuits. So there are a couple of AC power sources that can create alternating voltage, alternating current, and we'll be dealing with AC in different types of circuits. So a circuit with a power source of alternating voltage. Basically, just imagine a battery being able to slosh back and forth like a mass spring system, or a generator, you know, which are, you know, good sources of your AC. Power goes out, put the generator up. You know, just create some kind of alternating voltage source. And we're going to represent alternating voltage by this symbol, delta V, little v. And so this alternating voltage source is going to have alternating peaks of maximum voltage, basically the maximum amplitude of a sine function or a cosine function. And we've seen this before, like Q max in this associative wave function. So this would be a sample voltage function produced from an alternating voltage source like a generator. So this delta V max is the voltage amplitude. Just like in a mass spring system, if I pull a mass down to 2 centimeters, it's going to go up to 2 centimeters from +2 to -2. That's the maximum amplitude or the displacement. Same idea. This is a maximum voltage up and down. So in the previous chapter, we were kind of forcing or driving the oscillation. Now we're just going to put an alternating voltage source in the circuit, and it's going to do its own thing. It's going to produce the oscillation itself. So we don't have to do anything about it. And the solutions, at least in principle, that we were getting for the RLCs and others in terms of oscillations, will pretty much, in principle, be the same for our AC perspective here. There's a little couple of tidbits in there, but at least conceptually, we come out to be roughly the same thing conceptually, because we're going to be having circuits that there won't be just one direction for the current. Since the voltage source is going back and forth, it's alternating, the current is going to be simultaneously going, for a period of time, it's going to go one direction, then back the other direction, and forward, and then back, forward, back, because we have an alternating voltage source that's driving that alternating current across these different components: the resistor, the inductor, the capacitor. So AC sources include generators, which I'm buying one today, and electrical oscillators. You know, just anything that you can build that has an oscillation of electricity and create antennas. You know, could be electrical oscillators. Okay. Since delta V, little v, is from an AC source, the current also alternates. So this could, because there's, you know, they're directly proportional to each other. Delta V equals I times R. Your voltage oscillates, your current's going to oscillate. And resistor is a resistor. It's just going to be receiving all this stuff. Okay, it's seeing current go one way and going back the other way. The resistor is just sitting there. But when you think about it, like I said before, the power loss across that resistor is basically zero, because let's say you lose 2 watts in one direction. Well, you're going to lose 2 watts the other direction. Add them together, duh, zero. Again, that's the beauty of AC. And for so long, you know, even while Tesla was living, it got a bad rap. Edison tried to disprove that, okay, you can't use the AC, it's just bad for you, da da da. It's just a big time hater. And all these other fools, like Marconi, the guy that basically got the patent for the radio, he used about 10 patents from Tesla. And so when Tesla was, you know, somebody wrote him about it, he's like, it's all right, he's a good guy. He used about 10 or so of my patents. I mean, whatever. It's already been done. I'm going on to the next thing. I'm already, you know, building. He can have credit if he wants. But like, people were just biting off of him. Old term that basically means just stealing, using his stuff. He was the man, and they were jealous and envious. They just wanted to, you know, discredit him. And yet and still, we're using, you know, wireless communication, cell phones, you know, wouldn't be around if not for the work of Nikola Tesla. Nothing to do with Edison. It's his work, Tesla's work. You know, lighting up light bulbs wirelessly via your Tesla coil, because he understood how to transmit, you know, energy in an electric field over distance, power transmission. And you get that wave at a particular frequency, you know, frequency of light. You know, you light up your light bulbs, or definitely frequency at which that light bulb could resonate in the light frequency. Basically same thing. So yeah, he was the guy behind all that wireless stuff. He did it all. He's a radio guy, wireless, the father of the power plant. Just brilliant. Since delta V is from an AC source, the current also alternates. All right. So we're just setting things up here. And so from the first equation and what we've known before, omega equals 2 pi f, angular frequency, and that is equal to 2 pi over t, because frequency is 1 over a period. Power plants, you know, they design their devices to run at a frequency of 60 hertz. And that's basically kind of like the standard cycles per second of frequency of AC power sources. So let's go and look at how a resistor functions in an AC circuit. So let's take a diagram, something like this. And then we're going to represent our alternating voltage source by the sine wave because it goes back and forth. And then, so we're going to say that this is our delta V equals delta V max sine omega t. This is my resistor. So we've gone from your standard DC circuits to the most powerful AC. So now let's go to delta V. And now if we were to track, let's say the back and forth of this current, we could approximate this process by Kirchhoff's loop rule for voltages, where we have the power source indicated by delta V minus IR times R. And this is basically the current across the resistor times the resistor equals 0. So this is basically a situation where we could find the current at one moment in time, because remember, this is going back and forth. And so the solution here is going to allow us to find current instantly. You know, what's the current here, you know, it's like we can use any function of time, some variables function of time, like position as a function of time. Oh, I can find out where my mass on my spring is going to be at any moment. I can predict it. So we get this by Kirchhoff's loop rule. Where IR is the current across the resistor. And solving for IR is going to be delta V over R. That's from Ohm's law. I equals voltage over resistance. But now this is alternating. So this is going to be delta V max over R sine omega t. And this is principally current, where this is, you know, comes out to be maximum current sine omega t. So what we're going to see here from here, and then we're going to look at the inductor and the capacitor, and then all of them at once, if we, you know, have time to do that today. And that's where we'll stop with the RLC. What do we notice about the voltage function and the current function? As you're looking at that. That's the maximum current. Any guesses? Look at this function. This is the voltage function, and this is my current function. Anything similar or different about them? What do they have in common?
Sine omega t.
Yep. That means, and we'll see this in a moment, that means that they are in phase with each other. They are both dependent on the sine function. We're going to see with the capacitor and inductor that one has sine, one has cosine, you know, vice versa, stuff like that. So they're going to be out of phase. So this means, at least just looking at it generically, you know, generally, both of those quantities are in phase with each other because they depend on sine. And then I bring that up because we're going to take a look at something called the phasor diagram, which relates the sinusoidal nature of these quantities. So let's then just say I max is going to be delta V max over R. And that's when your sine omega t is approximately equal to 1. And that's, that's only going to happen at certain points. Sine is equal to 1 when omega t or theta is equal to, like, say, 90, 270. It's going to always be a max at those points. So what I did here is I'm just saying that this is a magnitude of I max, and it's going to be the same positive or negative. So it's like an absolute value, because remember the sine function is going to do like that, and so this is going to be your negative I max, and this is going to be your positive. So the square, deal with the square, but the values, they're the same amount in the positive or negative direction, whether the current is sloshing right or left. And so, you can look at this power loss deal in any way. The areas under those are basically going to cancel out. No power loss. Whereas direct current, you're going to be increasingly losing power, because that current is going to continue to go across that resistor directly in one way. AC, P equals 0. No power loss. All energy gained in the appliance or whatever is using the current. So pretty awesome. Okay, so this is basically an instantaneous voltage, this Vmax business, or delta V, across the resistor. So you find a voltage at any moment. Delta VR equals IR times R. That equals to I max R sine omega t. Remember, this was, Ohm's law. It was delta V equals I times R. Now we're doing it in terms of the sinusoidal nature of this voltage. So now let's take a look at this concept graphically. And so the graph, I and R on this in the same axis, and then we have, this would be a time. We're going to see that, let's see, we have this up here is like our I max. And then this is going to be our Vmax. And they're in phase, which means that they're, they're both sine functions. So if I'm going to do this, okay, I'm going to try to attenuate this, myself some guide. Okay, something like that. And then the current would peak out at the same value for time, and then goes to 0. So they're constructive. They're in phase. So this is in phase. They both have sine. They're both sine functions. Now, what we talking about this thing called a phasor diagram. So basically, a phasor diagram is looking at the vectorial nature of the voltage and the current. Oh, it's basically looking at it, like in terms of a unit circle, as it goes from 0 all the way around. And so we're going to compare the magnitudes of the voltage and the current by two vectors. And we'll see and represent this in phase thing with vectors. So from a phasor diagram, the current across this resistor and the voltage, or delta VR, can be represented as a vector for this this voltage VR, and then the current will be just a little bit longer than that. So this leg here, and they're both, you know, they have the same starting points. This would be the length of Imax. So Imax is all from 0 all the way up. And then this would be your delta Vmax. Or I can write this. So this diagram here is basically representing in vector form this stuff here. Phasor diagram. And this is theta or omega t. And we know that. Theta over t for velocity, angular velocity specifically, which is in linear form, linear velocity x over t. This is at one moment. At one moment, this is a moment. We're looking at this at one particular moment in time. That's your phasor diagram for a resistor in an AC circuit. So it's phasor diagram. You know, length of the arrows represents the size of the current in the voltage. So I think I'll save some writing on that. Kind of just talk about it. So the projections of these phasors determined by a sine function, because we know that they're both, these are both sine functions. Both in phase, they have their maxes and their mins at the same time, as we can see by the sine graphs. You can represent the overall magnitude of the phase by a vector diagram, but these are parallel or in phase with each other. That'll become more important when we'll take a look at how an inductor behaves in an AC circuit and a capacitor. Over one cycle, you know, the average value of both of these guys is going to be equal to 0. So you're gonna have the same area. So if I just completed it one more time, you know, because this is basically, you know, 1, 2, 3 parts, and we need a fourth part. Pi over 2, pi 3 pi over 2, 2 pi. And the average value of the areas underneath all of them will have to be 0. We're going to have the same 2 up and same 2 down for both the current and the voltage. So the time average is 0. The average for max and voltage is 0. Okay. So we get into this though. The direction of the current is no effect or affect. No effect. Yeah, no effect on behavior of the resistor. The resistor don't care. It doesn't matter. It's going to one way, because the resistor is seeing this as netting to zero. You know, it's like if it was one direction, okay, now it's continuously heating up. This thing's getting hot. You know, when you run something for a long time, warms, hot. AC is like, did net result is zero. It's hot, not as hot as the resistor in the direct current case, but the power loss is basically nothing. Okay, so that doesn't matter. Direction of the current has no effect on the behavior of the resistor. It's still going to be a resistor. So no matter the direction of the current, the temperature will not increase or decrease beyond the value. Basically, the temperature is going to be proportional to a current. If the current maintains, and it does, time averages out to be zero, and there's not going to be any increase in the magnitude itself, the temperature is not going to increase or decrease beyond the value of I. You know, so we're basically looking at T as a function of I. It's proportional. So you're getting a very efficient circuit with AC. You're getting maximum use for the voltage and the current with next to zero power loss. I keep alluding to that, but we'll see that mathematically down the line. So power in this AC or AC with a resistor, I squared R, where I equals instantaneous current because it's a function, it's a sinusoidal function. Instantaneous current, and instantaneous current, where the instantaneous current is, you know, proportional to I squared. So the direction of current don't matter because positive, negative squared, 2 squared or negative 2 squared is still 4. It don't matter. So the direction of I, not important. Right. So the thing to consider with AC circuits is this thing called RMS current, and then RMS voltage. So let's get to that. So AC circuit design is concerned with an average value of current called the, I'll do this, RMS current. Sorry about that. The root mean square current. And RMS is a concept that's first introduced in the kinetic theory of gases. We don't usually cover that in our physics classes, but if you look back at the kinetic theory of gases, this root mean square first comes up there. So we'll explain it, what that is here. So root mean square. Oh, don't you do that. Okay. Seriously, I didn't get a warning sign. It's not writing for me. All right. So root mean square current. So let's take a look at all this stuff because we've all right. So we've seen this Imax, positive and negative, right? So it's sinusoidal, something like this. Now we're not concerned with that because we know the time average is 0. So what root mean square is, it takes a look at the average of this up top, because you know it's all about. And so root mean square is basically going to be half of this maximum value. And so we're looking at this. So basically, we're going to chop this up in half. We're going to have this line going through here, and then we have another function. So let's take a look at what graphically root mean square is and explain it even further. Okay, so let me do this. Okay. So this is, if we take a look at average square. So I squared max here. And then this root mean square would be half of the max. So we're looking at over a period of time, what half of this I squared maximum is going to be. So basically, root mean square is half of the square, half of the maximum current squared. And let's see. Oh, I squeezed myself out of here. I squared average. So I'm going to do I squared average is equal to 1/2 I squared max. So this guy here is the one that's important. This is our root mean square. And graphically, that looks something like this. A little tighter sine function. And so this is going to be half, it's going to be another half, and so on. So we're concerned with the circuit designers in AC are concerned with this number as opposed to this max, because that's, who cares? Doesn't mean anything for us. This will mean something for you, especially since basically we're above the 0. We're in the positive domain always with this RMS. So RMS is going to be the square root of the average of this midline, this square root of this square, which is average current, and carrying it through even further, since I squared varies as sine squared omega t, because I is sine omega t, I squared is sine squared, and because average of I squared equals 1/2 of maximum squared, RMS current, square root of I squared average, it's going to be square root of 1/2 I squared max, and we get the RMS. This is going to bring it home. If this was here, it was all kinds of okay, sloshy and confusing. Well, let's take a look at it from the math perspective and understand it. The IRMS, this value is going to be √2/2 of Imax, or basically 70% of this, which we're not concerned with because it doesn't matter direction. So when we have a power outlet, or outlets, 120 volts AC, that's RMS current. That's what we were concerned with. This is we design our AC voltmeters and stuff like that with our RMS in mind. So really what's coming in is about 170 volts. You know, and we're just going to design everything to run on the RMS value. So this is equal to 0.707 Imax. Any questions on that? RMS is basically 70% of maximum current that we get from our AC voltage. Basically all RMSs. It whittles all after all that explanation. It just whittles down to about 70% of the maximum current. We need to do all the rest of the stuff in order to get here, you know. So let's say I have a current of 2 amps. Well, the IRMS, or the RMS current is going to be 70% of it. .41 amps. So our AC power source is going to be delivering 1.41 RMS. But we get the same power rating, which was, you know, again, allusion to the power. We'll get the same power even though the current is smaller, RMS. Same power as a DC circuit. Efficiency. This is all very efficient. So power to a resistor, then in terms of RMS current, RMS squared R, not RMS. This is RMS because that's what's coming in. And then therefore the alternating voltage, or that's the current that our device is going to be using, is the RMS value. Alternating voltage delta V max over rad 2, which is 70% of the max. So all this RMS, you know, we're concerned with the RMS, not the max, because max times itself out. RMS don't, right? Questions? I'll do a sample problem. I'm gonna take a breather. I do, but you know, we can keep on going. Any questions? You following so far?
Yeah, this math way, it really helps to understand.
Yes, always gonna come down to math. We're not gonna get away with it. Not English class, we're writing words everywhere, but just to explain things. But yeah. So, like as I was saying about the outlets, gives you more appreciation of what's going on around you. You know, you look at your power outlet, you have a better appreciation. Oh, 120 volts AC, that's RMS voltage, not the real. So outlets measuring 120 volts AC, that delta V, right, little guy, is an RMS voltage. So therefore, the maximum voltage is 120 volts times rad 2. So the maximum on a sinusoidal, you know, simple curve is actually 170 volts. But again, that times out to be nothing. We're not going to design our instruments to use the max, look at the RMS. So we're basically using a part of that voltage that is the RMS so that stuff can work. Stuff can work, you know. So that's that. And I was saying before, by using RMS voltage and current, circuits will still give you the same power. Same power as DC, as Edison. 1 second. Oh no, I'm wrong number for somebody else. So yeah, like I was saying, using RMS current and voltage, you know, in circuits gives you the same power as the direct current as Edison, but with less current and voltage. So you're not using as much current and voltage in your source, but you're getting the same power for one run, right? The IRMS squared times R. But overall, there is no power loss. No power loss. You're using less voltage, less current. So AC is a triumph. It's the best. You know. It's the best best circuit of the two. You know, best design. Okay, let's see. I have a few more minutes, and I'll set up this inductor. So this is going to be 33.3. We've now looked at how resistors operate in AC circuits. Let's take a look at inductors. Inductors and an AC circuit. So let us consider an inductor and the B field self-creator connected to an AC source, like a generator. So we have a little torus there. Generator, and that is my inductor. And so this will be the voltage across the inductor like this. And that's our little diagram. How's everything operate? We're going to go to voltage, to current, to the relationship of the two, graph it, look at the phasor diagram, and go on to the capacitor. Oh, one other note about this EMF is that, and you astutely pointed that out, Jeremy, and that's why I was trying to, see if you guys see that. The force that we saw, the net force, is analogous to the LD d squared Q over dt squared equals all that other stuff, right? This is possibly, or at least another way of thinking why people thought voltage was like another force, because that equation is the voltage across all of those components. And it's like the total voltage equals the other stuff. So that voltage is like the force equation in the mass spring system. So therefore, we're going to call it like the electrical force or the electromotive force. And that's probably one other way of another way of looking at this symbol E was electromotive force, the same as voltage. So we know across the inductor, we've derived this already. It's equal to negative L di, but in this case, DIL, represent another variable. And we saw this back in the other chapter, DIL over dt, and that's for an inductor. Yeah, we got all that. So we have Kirchhoff's rules, the voltage source, and then the voltage drop across the inductor equals 0. And we also know that delta V is equal to L DIL dt, set them equal, which is equal to delta V max sine omega t, which we saw before. Go, I guess I'll just continue on. Yeah, I'll just continue on here. Solving for DIL, or basically IL, we have DIL equals, solving for, the current, IL. So we have delta V max over L, okay, multiplied by dt, sine omega t dt. So we integrate both sides. These are constants, comes out. Sine omega t dt. This becomes IL equals, now, I'm not sure in your calculus books, it's got to be there. But the derivative of the sine function here, definitely I can have in my trusty mathematical methods book. Delta V max, I'm just going to give this to you. The integral of this is negative V max over omega L, 1 over omega, cosine omega t. It's basically the basis. Reminds me of the Fourier series stuff. But so IL, now we can represent this in another way. So delta V max over omega L, and we'll stop here. Sine omega t minus pi over 2. And we get that because it's an identity. Cosine omega t is negative sine omega t minus pi over 2. So if this is negative cosine is negative this, the negative cosine is positive that. So that's the expression for the current going through an inductor in an AC circuit. So let me just AC circuit current across an inductor. So then let's take a look at delta V, delta V max, sine omega t, and then we have IL equals delta V max over omega L sine omega t minus pi over 2. And that's also equal to negative delta V max over omega L cosine omega t. It's just the relationship here. So we can see as we close for the day, today is that delta V is proportional to a sine function, and the current is proportional to a cosine function. So there's going to be a lag between the voltage and the current. In this case, they're not going to be in phase. So I'm going to quickly draw this, and we can continue next time. So the current is going to lag by pi over 2. That's why this negative pi over 2 is here. You know, the mathematical description and stuff. So there's I max, delta V max. Let me just go ahead and see if I can do this. That's for my delta V. And then my current is going to lag by 90 degrees or be in the negative pi over 2 area. And it's going to go like this. So when this is max pi over 2 before this guy's max. And then he comes through like that. And then, you know, kind of splits up. So this is clearly out of phase by pi over 2. Oh, I didn't quite get up there, but yeah. So I'll leave it at that. We'll continue on, backtrack on this. So good. Any last thoughts, last questions? Hope you found this fun, at least conceptually, if not the whole way.